Okay, everyone, so let's go into our lesson on vector addition. Back to the narrative. Any object's motion can be described in displacement, velocity, and acceleration. And before we can get there, we have to talk about vector addition. We're almost there. Just kind of have to get that out of the way, and then we can talk about speed, velocity, and acceleration. So let's go ahead and do this real quick. So kind of vector addition, vector A plus vector B is going to give us vector C. If I give vector A between these parallel lines, it means the magnitude of vector A. It kind of means drop the direction and just tell me how much is vector A. Simple enough. Let's go ahead and give a quick example. I just drew in my x component, drawing in my y component. What would be my resultant? From the tail of the first one to the head of the last one, we keep this kind of head to tail notation, and that would be C. Go ahead and make sure you kind of keep your typical head to tail notation, and you should be in good shape. So let's talk about where, according to this narrative, we would use some vector addition. And we should keep on going back to the narrative because that's what the new MCAT is all about. So when and why do we add vectors? Well, kind of the primary reason is systems are really complex. You're going to have multiple forces at play in different directions, different magnitudes, and we often want to summarize that into a single force that's kind of easy to handle. So systems are complex, especially living systems. You can have many forces at play, and the last thing is you can have a feedback loop where certain forces lead to more forces kind of acting on the same system or at the same location. So you want to make sure that you can kind of add all of those forces together, and it could be kind of any vector. So it doesn't have to always be force. It could be kind of an acceleration, or it could be a velocity. So let's go ahead and talk about what we need to know. So what we need to know is it's usually just kind of exactly like we did for the previous lesson. It's usually just some triangle geometry, and it's usually kind of right triangle geometry. And you're going to have kind of this F net, and that F net is going to be the sum of a certain number of components, and we're going to kind of summarize all these components. And I'm talking about kind of the water flowing up a plant. You could have kind of one of these could be force gravity, and that's going downwards, and the other one could be kind of capillary action, and that's going upwards. And you could have kind of a slaw of other forces, and some of them would be positive, and some of them would be negative, and some of them might be acting kind of straight vertically, and some of them wouldn't be. And you're going to have kind of all of these. Okay, so let's look at a quick example. We're going to have a bird that's flapping its wings, and it's doing so that it would kind of go north at 10 meters per second. That's kind of if there was no wind. But I'm going to introduce kind of an eastward wind, and I'm going to put the eastward wind at 4 meters per second. And then my question would be kind of asking what would be kind of the actual direction. What's kind of the V net if you had these two kind of things at play? Simple enough. Let's go ahead and kind of draw it in real quick. Go ahead and make kind of my y component, my x component, and I'm going to go upwards because I'm going north, and then I'm going to go to the right for my x component because that's kind of how we usually conceptualize going to the east. And we just got 4 and 10. Simple enough, kind of just some right triangle trigonometry. Nothing crazy happening here. I'm going to draw my resultant in. I kept my kind of head to tail notation, so my last head, so kind of my total direction, as you would guess, is going to be this kind of northeast. And maybe I want to know kind of which direction and with which magnitude. So just kind of a simple right triangle geometry. I'm going to use the Pythagorean theorem, and I get that V net is the square root of 116. I might want to kind of simplify that, so I can kind of say, well, 116 is 4 times 29, and the square root of 4 is just 2, so I get 2 square root of 29. That's great. But maybe I want to know what direction it is, so it's kind of also just kind of an inverse tangent of y over x. I get kind of tan inverse of 10 over 4, and that's good enough for the MCAT. You kind of wouldn't be expected to solve that. You could say kind of tan inverse of 5 over 2. So we mentioned this in our last lesson, just kind of a brief discussion of whether or not we need to always kind of break things into the x and y components. So to add two vectors, do they always have to be kind of these perpendicular, making a right angle? And I'm going to quickly kind of show you guys that that doesn't have to be the case. Any two components that are kind of head to tail can always kind of have a resultant, and they always do have a resultant. You just kind of connect the two lines and you come up with kind of a triangle, and then you can do kind of right triangle trigonometry, or in the easy case, but in kind of the more complicated case, you might have to use some of the more complicated kind of law of cosines, law of sines. It's not really kind of something you need to worry about too much for the MCAT, but you can have it kind of just in your bag of tricks and kind of know that it's possible. So I'm going to make this red vector kind of my resultant, and these two blue vectors my two components, and they kind of don't make a right triangle. And if I was kind of asked for kind of the magnitude of C, and C is kind of my resultant, I know that A plus B definitely do add up to C. They kind of make a triangle. It's very clear that everything works head to tail as expected, but just not kind of extremely easy to calculate what C is. But I can kind of just set up my law of cosines, a squared plus b squared plus 2ab cosine c, and then cosine c, you need to kind of angle c, and angle c is the angle that's across from side c. Just kind of keep it in mind, not something that you need to stress about too much. Well, we've seen that we can break kind of vectors down and that we can add vectors, but we can also subtract vectors. So vector subtraction is really simple, so let's go ahead and get into that real quick, and we can see that a minus b equals c, no problem. And to solve this, the easiest way to operate is to say a plus negative b equals c. So you might say, well, what does it mean to have kind of a vector negative b? And that's simple enough also. Negative b just means kind of the b vector, and you kind of just flip the direction. So if I kind of made this vector to the left, if I made that b, I would make negative b the exact same vector, but just going in the opposite way. So that's simple enough. It just kind of means that if you're going to subtract a vector, whatever one kind of has the minus sign, you're going to go ahead and flip its direction. I can actually probably just do this on one Cartesian plane. Go ahead and draw in my a, and I'll go ahead and make my a going upwards. And I'm going to draw in b, and I'm going to draw in negative b. So b is going to go to the right. Simple enough. And then my resultant would be this kind of northeast direction. And then negative b would go in the opposite direction and have the same magnitude, but it would go to the left. And then my kind of new resultant would be in this kind of northwest direction. So simple enough. Kind of the one on the left would be kind of a minus b, and the one on the right would be a plus b. And I really can't stress this enough that we should always be asking ourselves, how does this relate to living systems? So vector subtraction is most relevant to negative feedback loops. Basically, any time that you need to flip the direction of a vector. In a negative feedback loop, you could have an instance where multiple kind of positive direction vectors lead ultimately to something that's kind of operating in the complete opposite directions. You might say, how do I add kind of multiple things going to the right and eventually get something going to the left? To do that, you use vector subtraction. The last topic we're going to talk about is vector products with scalars. So this is kind of under the umbrella of vector addition, but a little bit different. We're going to take c to be a scalar, and scalar just means that it doesn't have a direction. It could be kind of any number, 1/2, -5. Let's talk about the properties of CA. So CA is going to have the same direction as A for the most part, and we'll talk about that kind of in a second when that breaks down. The other thing is that kind of the magnitude of CA is just kind of equal to the magnitude of A times C. So if kind of C is 5, the magnitude of CA is 5 times what the magnitude of A was. The third thing we kind of need to know is actually kind of a direct result of the second thing. That is, if C is bigger than 1, then kind of CA got bigger. And if C is between 0 and 1, then it got smaller. If C is 1/2, kind of the vector was cut in half. The last thing you need to know is that if C is negative, it flips directions. It flips directions in the sense that the magnitude is now flipped. So that's the case where 1 breaks down. If C is negative, it has the same feel, but it goes in the complete opposite direction. Let me show you a quick example. So I'm going to draw kind of my original A vector on the left in blue. And I'm going to draw kind of my adjusted vector that has a scalar product. So my original vector is going kind of up and to the right, and my kind of new vector is going down and to the left. And this would probably be C is negative 1/2. It's definitely shorter, and it's going in the opposite direction. So that's it. Thanks for watching. Please like and subscribe for more videos.